like to begin by acknowledging the traditional owners of the land in which we meet today. I would like to also pay my respects to elders past and present. My name is Mahmoud Ismail. I'm a Senior Technical Account Manager at AWS, and I help support customers with their cloud journey. I'm delighted to share the stage with Paul.
Hi everyone, my name is Paul Rapper. I'm a Senior Staff Software Engineer at Slack.
And welcome to our session, how Slack built resilient architecture to support real-time messaging. For today's talk, I'll talk about a typical customer journey and what some of the challenges we see customers face. I'll then talk about some key resilience concepts like fault isolation and multi-AZ patterns and cellular architecture. And then Paul will take you through the Slack case study and what they did on their resilience journey. So what does a typical customer journey look like? It usually starts when a company or an organization experiences high impact incidents. This will raise some eyebrows within the organization, which will lead to a business mandate to improve the overall resiliency of the infrastructure and architecture. A program of work can be introduced to look at fault tolerance and high availability. And then the question will be asked, how do we recover from incidents when they happen? And along this journey, we see customers face the following challenges. Blast radius. A big blast radius can really impact your business. And it's important to understand how you can reduce your blast radius. Fault isolation. How do we contain the failure to be within a single boundary and not cross any other boundary? And then this failover. Once we've identified the fault, how do we mitigate? How do we move away from this impairment? So with those challenges in mind, let's first discuss fault isolation boundaries. What is a fault isolation boundary? Basically, it's a way to contain the failure to be within a defined boundary. Anything within this boundary, anything outside of this boundary is unaffected and will continue to function as normal. From an AWS infrastructure perspective, we have regions. A region is a physical location around the world, and every region is independent from another region. And in fact, a region is a fault isolation boundary. Zooming in, a region has multiple availability zones, or AZs, and every AZ is a fault isolation boundary with lots of data centers and high levels of redundancy already built into it. It's important to know these boundaries that are available to you so you can architect your workload in such a way you reduce the impact of a failure when it does happen. The focus of today's talk is AZs, availability zones. But if you'd like to know more, please scan the QR code here and it'll take you to a link about fault isolation boundaries and go into more detail. Let's talk about some failure scenarios. In a traditional multi-AZ architecture, you are protected from some common failures. If an AZ is impaired, multi-AZ is a good solution. If a rack goes down, autoscale groups can help spin up new instances in a different rack. There's two failure scenarios that I would like to discuss with you today. Bad deployments and great failures. These are two failure scenarios that, if you haven't carefully planned for it, could really impact your business in a big way. An example of a bad deployment is when you deploy a new version of your application out to your infrastructure. And on a bad day, you could introduce a poison pill behavior, where a client will send a poison pill that's load balanced and distributed across multiple availability zones, hence affecting all your resources, triggering an application bug. Because of this scenario of having cross-AZ load balancing coupled with the multi-AZ architecture, the fault and the failure has been cascaded across all your AZs, across all your resources. And so the question is, how do we reduce the blast radius here? Is there a strategy that we can use to isolate the fault and apply fault isolation? Let's take an example of great failures. Let's say we have a system that is a dependency for 3 consumers, application 1, 2, and 3. Each application is doing its own monitoring, but it's also sending the latency metric to a core business logic that in turn sends a report to the observer. And the observer sees the average latency across all 3 consumers. And in this case, it's 53 milliseconds. The system also has a reactor function, and this has a configured latency threshold of 60 milliseconds. Now, if the average latency exceeds this threshold, the system will trigger an alarm signifying that there's an issue with the overall architecture. There's a failure somewhere that's been detected. So right now, as it stands, monitoring is showing that it's green, and in fact, everything is green. Application 1 sees increased latency. If this application is a real-time application, user experience will be bad from a voice and video quality. If this was a microservice architecture, then there could be the potential of a cascaded failure because of inter-service dependencies. So now application 1 is obviously going through some pain. The average latency is increased to 59 milliseconds. What you'll see here, that this number is still less than the latency threshold, meaning the monitoring is telling us that everything is fine, everything is green. But as a matter of fact, application 1 has seen an increase of 40% latency. So there's an obvious discrepancy here. Application 1 is seeing something different, and the problem is application 1 is relying on the monitoring of the system. And this is what we call grey failure, right? Different entities are seeing the failure in a different light. So what application 1 should really do, and the rest of the applications here, is not rely on the system. And in fact, it should do its own detection and mitigation of the failure. So the question is, how do we reduce the impact of this failure? What should the consumers do in this case? Bringing these two failure scenarios together. For bad deployments, we could reduce the blast radius by looking at safe deployment strategies, like canary or blue-green or staggered deployments. For grey failures, we can use a combination of AWS services coupled with health checks to detect any issue that may be apparent and to do the right course of action as a result of that. There is one strategy that applies to both scenarios, and this is what we call AZ affinity. So before I tell you about what AZ affinity is, let me tell you about cross-AZ load balancing and the problem that it has. Let's say you have a load balancer that's sending traffic across multiple availability zones. And let's say there's an impairment in one of the AZs, in AZ3 in this case. Because traffic is being load balanced across multiple availability zones and touching all endpoints, an observer will notice a 33% degradation across the board, across all AZs. And a false assumption can be made that the entire region is faulty, whereas as a matter of fact, it's only one AZ that's affected. And so the solution to this is AZ affinity. And what this is the ability to pin traffic. You pin the traffic to remain within an AZ and not cross any other AZ. So now in this situation, if there's an impairment in AZ3, an observer will notice 100% degradation only coming from a single AZ, as opposed to the previous example where it wasn't apparent where the issue was coming from. And a valid conclusion can be made that a single AZ is impaired. And this is very important. If you could deduce that a single AZ has been impaired, it's easier for you to mitigate, and we'll come to that later. And this is what influenced cell-based architecture. And in our case, one cell equals one availability zone. And the idea here is to make multiple copies of your entire application stack and deploy that in every single AZ. And important note here, do not have any cross dependency between these cells. And in this way, data is partitioned where there's no replication between the cells, there's no cross dependencies, giving you complete isolation and a way to isolate faults to contain within a particular cell. So looking back at our challenges again, we can address blast radius and fault isolation by using cell-based architecture and AZ affinity along with a safe deployment strategy. This leaves us with failover. Now that we have identified a single AZ as being impaired, what's the next step? So when we detect a single AZ failure, and now we have the right architecture in place, we're able to pin the traffic to remain within a single AZ, we have cell-based architecture, it makes identifying the fault much, much easier. And we could deduce that a single AZ has been impaired. Now, the next step is mitigation. How do we evacuate the AZ? And you can see now that we're pinning the traffic, you can see how this makes life easier because you have identified which AZ is impaired. In 2022, we launched a feature of application recovery controller called Zonal Shift. Zonal Shift allows you to specify an AZ ID and a resource ID. And effectively what it does is it takes that AZ out of service. What we're doing under the hood is manipulating DNS to stop returning the IP address of that load balancer from that impaired AZ, leaving the remaining AZs to forward traffic. This is the recommended way of doing an AZ evacuation today, and what the most cost efficient and most effective way. And it's what AWS recommend doing today. And now, revisiting these challenges again. Using cell-based architecture with AZ affinity, along with safe deployment strategies like canary deployments and staggered deployments, along with having an AZ evacuation strategy, something like Zonal Shift, it was able to address all the challenges that I've outlined for you today. Okay, and with that, I'd like to introduce Paul to the stage to talk about their resilience journey and what they did. Thank you.
Hi everyone. As Mahmood mentioned, I'm here today to talk about Slack's journey to cell-based architecture and focusing on our egress stack. So I'm sure some of you are wondering, why are we running our own egress stack and not a managed service? Our network design predates the usage or creation of AWS Network Firewall, and at the time, our network volume exceeded the capacity and capability of NAT gateways. So we had to build our own custom solution. The solution we decided on was to build a stateless fleet of squid proxies, which are used to provide internet connectivity for all of Slack services out to the internet. So that's if you paste the URL into Slack and it unfurls, or it makes an API call to, say, the Google Suite or wherever that is, that traverses through our egress cluster. So in terms of setting the size of this migration, the egress cluster currently operates in 15 regions throughout the globe. In those 15 regions, we have 103 unique clusters. A cluster is made up of a number of cells. For example, our image proxy cluster in AP Southeast 2 is made up of 3 cells, 1 cell per AZ. Gives us a total of about 486 cells globally. At our peak, our busiest cell peaks at about 70,000 requests per second during US business hours and hovers at around the 30K base peak load. So why do we want to move to a cell-based architecture? Overall at Slack, there's an ongoing body of work to move our critical infrastructure to an AZ affinity architectural pattern. This in turn is being driven by a reliability goal where all customer impact is remediated within 10 minutes of a failure in our critical path. Continuing on with the reliability theme, we want to provide a safe and easy way to make complex changes to our egress environment. And finally, the egress environment is quite large and our costs have exceeded our budget, so we've got some cost control work to do there as well. So where did we start off with? We start off with a very simple design. We had a single Route 53 DNS record pointing to an NLB, which was a multi-AZ NLB that had cross-zone load balancing enabled. We then sent all the requests to a fleet of EC2 instances, which were then managed by autoscale groups, and we had scaling rules and healthy thresholds. That all worked until we outgrew it. The next iteration was to take that single cluster and stamp that out multiple times in a given region. This allowed us to then route certain traffic from certain request paths to certain clusters. This gave us 2 main benefits. One, it improved our horizontal scalability of each individual cluster, as each cluster was now able to scale independently of one another. And then it also improved and reduced our blast radius. So if a workload took down one of our clusters, it only impacted that singular cluster and didn't cascade through the fleet. At this point in time, all our clusters globally are identical. And within a given single region, all our clusters live in a single Terraform state file, which kind of led to that problem where we were unable to safely and easily deploy a change to a single cluster without causing another outage. So the brave new world, cell-based architecture. For Slack, a cell is mapped to an AZ, and then we also refer to that particular cell as a shard. What we ended up doing was taking a full copy of our full existing egress stack and making that self-contained within a cell. So each cell has its own DNS entry point, its own load balancer, EC2 instances, autoscale groups, health checks, and all the bells and whistles. We then placed a new DNS record at the top of all the cells that span and make up a cluster, and we leveraged Route 53 weighted DNS and DNS round robin to evenly distribute the traffic across all the cells that make up the cluster. So what happens when something goes wrong? As you can see here, something has gone wrong in AZ1. Our Route 53 health checks has realized one of its dependencies. In this case, AZ1 has gone unhealthy and simply stopped sending traffic to that AZ, and we've evacuated that AZ. Now, workloads within Slack that are using that top new level DNS record we created are not impacted by this change. Their requests simply fail over to another cell and things continue to operate as normal. However, services that access the cell-specific DNS entry point are now experiencing an outage, and they have to do one of two things. The service either needs to evacuate themselves out of that AZ or handle the failure gracefully on their own. So how did we migrate from the old world to the new cellular world? Reliability was priority 0, 1, and 2 for us during this migration. Keeping Slack up and running and available was at the forefront of every decision we made through the entire process. Every change we made had to be a two-way door with a super easy, quick rollback. By leveraging Route 53 weighted DNS to control the traffic from the old stack to the new stack, essentially blue-greening our deploy, and doing so in small, incremental, and controlled ways, allowed us to do this. Again, by leveraging Route 53, we were able to do a rollback in under 90 seconds. We had a philosophy during this migration that if it was perceived at any point in time that the egress cluster migration was the cause of any problem, we simply revert the change, roll back to our last known good state, and then one of two things would happen. Either if we were at fault, customer problem would go away, or we would just be told you weren't the root cause, continue on with your migration. As I mentioned at the beginning, we operate these egress clusters in 15 regions. This allowed us to use the off-peak and less critical regions and less critical clusters in those regions to test, validate, and verify all our deployment processes, our troubleshooting skills, and our rollback procedures before we got to our mission-critical clusters in US East 1. So let's go back and revisit the problems and see how we went. So Slack's infrastructure moving to an AZ affinity architectural pattern. This is a tick. We now have the ability to run a complete isolated egress stack in a single cell, and we now have the ability to evacuate a cell or multiple cells in an AZ if required. Remediate customer impact in less than 10 minutes from a failure. So as we can see here, there are two screenshots from our Slack that our automation posts in there when a cell is evacuated and then when a cell is returned back into service. In this particular case, we were doing some security patching for the instances in a cell, and we were rotating the nodes a little bit too aggressively. What happened? We have a CloudWatch alarm that monitors the number of healthy hosts we want to have as a minimum in our cell. That alarm went critical. Route 53 health checks noticed that and immediately drained that AZ, or cell in our case, out of service. It then notified us and paged us. The on-call engineer would have investigated, realized that we were the root cause of that problem, and slowed down the rotation process. The alarm would have then recovered, the cell would have been placed back into service, and then back into normal capacity constraints. The key takeaway right here is we remediate customer impact as soon as we are aware, before a human is involved. That has been a game changer for us and gives us lots of confidence in our later slides where we're actually making our changes. So, reducing our egress costs in line with our budget guidelines. As I had mentioned earlier, all our clusters globally were unique. That includes instance size and instance type. We now run a very mixed fleet across the globe with specific instance types and families targeted for specific workloads and their profiles. We also have the ability now to run a mixed fleet of instances across a cluster, as we can use different profiles for different cells as they are fully isolated from one another. This has been amazing for us, especially dealing with instance availability across AZs against the newer instance types. Finally, a big cost saving for us was cross-AZ traffic that we saved. We found that once we got the traffic in a cell and kept that traffic within that cell, we reduced our cross-AZ traffic by 60 to 70%. This was totally not planned for and totally accidental, but it's a win and we're taking it. And finally, we wanted to provide a safe way to make complex changes to our egress infrastructure. We now have the ability to deploy an infrastructure change to a single cell in a cluster. We then have the ability to watch metrics against that cell and compare that to another cell in the same cluster whilst they're both taking the same amount of traffic and being able to compare them side by side. This, coupled with our now found confidence in our automation process to evacuate an AZ, it's very easy for us now to make aggressive and slightly risky changes to a single cell, knowing we can extremely limit blast radius to that one cell. So, in a migration of this size, not everything goes to plan. A few things we struggled along the way that I'd like to share is around our monitoring and alerting. We found monitoring a service at a cell level to be extremely difficult at the beginning. We started off having to improve our logging and metrics pipelines to start understanding the concept of a cell. We then had to go and update all our logs and metrics we were emitting as a platform to apply that new cell-based metadata. Once we did that, we had to then go and rebuild all our dashboards. We had to create essentially two views of the world. One view which was drilled down and specific to the health of a single cell and view that in isolation, but then also at a cluster level where we would have to aggregate certain metrics across the cells that make up that given cluster. Once we got that, we introduced our own next problem, which was notification storms. At the very beginning, we had misconfigured a few alerts that instead of placing them at the cluster level, we put them at the cell level, which meant when something broke, we got 6, 7, 8 times the amount of pages than what we should have got it. That was a lot of trial and error, and we're in a much better place now. Finally, the big problem we hit along the way was our deployment mechanism. We went from a platform where we were able to deploy a change globally to all our egress infrastructure in about 15 stages, to one now where there are over 100 stages and lots of manual clicking that needs to happen along the way. It's not great, and it's something we need to look at. So what's next for Slack and our egress platform? As I just mentioned, we need to reduce that deployment pain that we caused. Having someone clicking a button 100 times to get a change out is not good for anyone. We also want to investigate the usage of Route 53 application recovery controller to do a lot of the evacuations for us in both planned and unplanned scenarios. And finally, we want to investigate leveraging a managed service, in this case, AWS Network Firewall, as a straight replacement for our entire egress stack. So if you'd like to know more, please take a look at our Slack's engineering blog, slack.engineering, or scan the QR code that's up here. And with that, I'll pass you back to Mahmood.
Thank you for sharing your journey. That was
Awesome. And to summarize, have a look at cell-based architecture and AZ affinity as a way to reduce your blast radius and apply fault isolation in your environment. Reduce your blast radius by looking at safe deployment strategies like canary deployments and blue-green and staggered deployments. I talked about grey failures earlier, so make sure you have the right monitoring and observability in place to be able to detect those kind of failures. And lastly, have a strategy to evacuate the AZ once you've identified that AZ is impaired. Don't forget to visit Skills Builder for all the great content and hands-on lab to upskill in your AWS cloud. And with that, we'd like to say thank you for attending our session. And please don't forget to rate our session on the mobile app. Thank you so much.
Thank you, Mahmood, and Paul, thank you very much.